Hello everybody, I'm Yu Tian. I'm an MS student in Applied Statistics at Westchester. So this is my paper about introduction to the process of improving a neural network. It joined the Midwest SOC 2018. So for this paper, we have 11 objects. For object 1, I bring data into Enterprise Miner. Object 2 is a replacement node. Object 3 is an input node. Object 4 is a variable clustering. Object 5 is a variable selection. Object 6 is a data partition node. For Object 7, identify the 22 different auto-neural nodes that we run. Object 8 is a transform tab. Object 9 is a decision tree. Object 10 is a data export node and deep neural net. Object 11 is a model comparison node. So I have to go fast. The paper has more details. Let's go to the first one, bring data into Enterprise Miner. This is our data. A consumer credit company wants to take over the process for approval of nodes and to automate the approval process. So in order to attain this target, we use home equity dataset, which contains 5,960 observations on node performance. The target Y is bad. Bad is a binary variable, including whether an applicant paid or no, or was delinquent. Just follow the red arrow. For each applicant, we have 12 input variables were recorded. So this is object 2 is a replacement node. The function of a replacement node is to trim or replace value. Her first variable is age of oldest credit account in months. So we trim the variable or replace outliers with more reasonable values. In this example, we trim the right edge of the distribution when value equals to 492. Then we will replace all values in the outliers of the distribution, which value greater over than 492 with upper limited value 492. Although the point 492 is far away from the middle of distribution, but there are almost 200 applicants with a value of 492, so we assume this point probably has an important impact on bad. You can see this is outliers. So fix all variables before splitting the dataset, so all observations are fixed with the same business rules. This is number of credit lines. For number of credit lines, we trim the right edge of the distribution when value equals to 53. For the debt-to-income ratio, we trim the right edge of the distribution when value equals to 75. For the derogatory credit reports, we trim the right edge of the distribution when value is equal to 3. For the requested no amount, we trim the right edge of the distribution when value equals to 50,500. For the existing mortgage amount, we trim the right edge of the distribution when value equals to 250,437. For the number of credit inquiries, we trim the right edge of the distribution when value equals to 5. For the value of current property, we trim the right edge of the distribution when value equals to 340,000. So for years on job, we trim the right edge of the distribution when value equals to 32. So let's go to the object 3, is an input node. We can see this figure shows how SAS handles class and interval missing values. We would like to impute the reasonable values for observations that have a missing value. Many of modeling techniques will discard a complete row of data if one of the variables in the model has a missing value. The input type in Enterprise Miner that imputes missing values has an incredibly convenient feature. You just follow the red arrow. So the fact that the enterprise miner will build a separate decision tree to impute missing values for each of the X variables that have missing values is a great time saver and increases the number of observations that we can use in the model. So now let's go to the object 4, variable clustering. For the variable clustering, some of the possible X variables are redundant with other X variables. Redundant X variables introduce multicollinearity, increase runtime, and violate our goal of parsimony. We can use variable clustering to remove them before the modeling process starts. These figures give some idea of how SAS clusters that variables and which variables SAS considers to be close to each other. After running the variable clustering tab, 18 variables, including categorical variables, are assigned to 7 clusters. This is first one, second one, third, fourth, fifth, sixth, and 7 clusters. This is an enlargement. SAS assigns cluster numbers. Just follow the yellow stars. So this figure displays a horizontal tree diagram from SAS Enterprise Miner and shows how the clusters are created. The ordered variable names are displayed on the vertical axis. Let's look at these star marks. We found 7 clusters. So the horizontal axis displays the proportion of variance in the dataset explained at each clustering level. So this figure shows details of how the variables are clustered. For example, the first cluster contains 3 variables: module, value, and no. This is thus displays the R-squared value of each variable with its own cluster and the R-squared value with its next cluster. SAS has 2 rules to choose place a variable in a cluster. First, the R-squared value for a variable to other variables in its own cluster should be high. Second, the R-squared value for a variable with next cluster should be no. So we should consider both rules together. Please look at the column 1 minus R squared. It displays the ratio of this formula for each variable. Smaller is better. So for the cluster 1, SAS kept that the best non-redundant variable. You just see the yellow highlighting. Now let's go to the 5th, variable selection. After we have removed redundant variables, the SAS variable selection tab uses several steps to remove non-predicting X variables. First, Enterprise Miner computes the squared correlation between each variable with a Y variable and rejects variables that have a value less than a minimum R squared. Second, Enterprise Miner uses a forward stepwise regression using R squared as a criteria to determine the importance of variables in a future model. SAS automatically creates interactions and can create dummy variables. So we can see there are 8 variables, including 2 group variables that are interaction, kept in the model after running the variable selection in SAS Enterprise Miner. So variable clustering is not a technique that identifies important predictive variables. That technique just checks for redundant variable and in some ways similar to a factor analysis. Variable selection and decision tree both create measurements of how important a variable is in predicting a Y value. They use different geometries and different algorithms that they are not expected to agree 100%. So I compared output. Because the variable selection technique is so powerful, I decided to use output from the technique as input into the neural networks to follow. Now let's go to the 6, the data partition node. For the data partition node, we split after cleaning the data, so all observations have the same business rules. We use this node to split data into tree, validate, and test. The ratio is 0.5, 0.25, and 0.25. This is our data set allocation. This is partition summary table. So now this is the 7th. It identifies the 22 different autoneural nodes that we run. In this part, I use 5 hours runtime on a laptop, 2 hours for cooking, 2 hours for study, 1 hour for sleep. After I wake up, I find it works for my laptop. Now, we build 22 neural networks using autoneural node to evaluate different structures and transform functions. The autoneural node has a promise of being a powerful and huge time saver for analysts. The autoneural node promises to evaluate many different neural net structures and many different transforms inside those structures. I run 22 autoneural nodes in this paper. The first reason was to try and create enough examples so that effects of different parameters could be deduced from the output of the 22 different runs. The second reason, because the link between parameters and the neural network structure was hard to determine. So I wanted to do enough neural nets so that the best structure would be selected. So some parameters we changed. First is type, we have 4 types: funnel, block, cascade, and linear. And this loads. For this progress, I set 4 different kinds of loads: 1 node, 3 nodes, 5 nodes, and 8 nodes. For the frozen, we froze connections between 2 nodes when we use cascade structure. This is some other settings. I set maximum iteration is 50. And total number of hidden units is 30. So for the autoneural produces 4 structures. This is single structure. This is block structure. This is funnel structure. And this is cascade structure. So next step, we will go to the transform tab and decision tree. So first, as we all know, y is defined unknown. We had to use a transform node to rename the variables so we could read them on a tree. We created this decision tree to provide a benchmark for comparison that we could use to judge the many models that we run use neural net technology. We paid particular attention to variables that the decision tree considered to be important. We wanted to see if the other SAS techniques would identify the same variables as important. We're also very interested in seeing if we could identify interactions that were high enough up in the tree so that we might be able to code them manually in a logistic or regression model. So for the variable importance table is shown at the right side. We can see the decision tree is very large and very difficult to present. So we are very pleased to see the ratio of importance for validation and training to be so high. This is mortgage. With this ratio of 0.5371 is only variable that shows much difference in importance between training and validate dataset. And then variables having different levels of importance. Small ratios are bad in training and test dataset, suggests that the dataset are not similar, that the cast doubt on the effectiveness of the model or the test dataset. Here is an enlargement of the top of the decision tree. Y is default on no. A decision tree splits the dataset into groups that are more homogeneous. A white leaf has a higher percent of defaults, and a blue leaf has a lower percent of defaults. The variable number of delinquencies is the most important variable in splitting observations into people who pay of the no and people who don't pay of the no. If the number of delinquencies is less than 1.78, a subject will go to the left. If the number of delinquencies was greater than 1.78, the subject will go to the right. Now let's go to the Object Turn data export node and deep neural net. For this part, I use ProgNeuro to build two deep neural nets. The difference between the two deep neural networks is that one uses an activation function of tangent edge, and one uses an activation function of linear. Both neural networks use a funnel structure starting with 8 nodes. Just follow the red arrow. We can see the program is too huge and long, so I just show part of the SAS program in this slide. More details are in paper. So now let's go to the last one, model comparison node. We use model comparison node to compare the output from the 22 autoneural nodes as a one decision tree. You can see this table. Importantly, we had a preference for doing deep neural networks in the SAS display manager and had to do a manual comparison. The fit statistics from the comparison node show that AutoNeural 13 had the best output because the lowest misclassification rate, though not much better than AutoNeural 22. For the enterprise miner also produced some very attractive output, such as ROC curves. The ROC curves, we can see the right side, show AutoNeural 13 is green line, AutoNeural 22 is blue line, and the best models for train, test, and validate datasets. Because we had enterprise miner partition the dataset into 3 parts, enterprise miner, without us having to do anything, produced 3 ROC curves. SAS understands that basic classification rate assumes equal penalties for the two types of mistakes. Although SAS Enterprise Miner in several procedures allow an analyst to set different penalties to be associated with a bad no versus not giving a no to a good customer. But not here. I didn't have time to explore this. I just used misclassification rate to analyze confusion tables to select the best model. I will compare 4 confusion tables, which including AutoNeural 13, decision tree, deep neural net with linear model, and deep neural net with tangent edge model. Because of my limited experience with Enterprise Miner, I have to copy the predicted status dataset from AutoNeural 13 and decision tree into Excel. I created this table manually, though I'm sure there is a better way. I think confusion matrices are an excellent tool for judging model quality. This is a confusion matrix. Importantly, confusion matrix for AutoNeural 13 is above, and the misclassification rate of 0.164 and misclassification rate of give a bad no is 61.745%. AutoNeural 13 would result in our giving a no to 184 people. Who wouldn't pay the no? I think the cost of giving a bad no is much more expensive than the cost of not giving a no to a good customer, and now say that AutoNeural 13 might not be the best model to use. Here are the confusion matrix for the two deep neural nets. The left one is funnel linear network. The right one is funnel tangent edge network. This is actual pay no and actual default for both tables. And this is predicted pay and predicted default. So both of them is a funnel structure with 8 nodes in the first hidden layer. One uses a linear transform function and the others use tangent edge. I think the cost of giving a bad no is much more expensive than the cost of not giving a no to a good customer. I will pay more attention to the value of give a bad no. We can see the red box. The smaller means the more expenses could be saved for the complaint. So the misclassification rate of give a bad no is 75.5% for linear network, 55.47% for tangent edge network. It means we will select funnel tangent edge network, comparing these two deep neural net models, which can save more money for the credit complaint. Now, at the right side is a confusion matrix for the decision tree. We can see the misclassification rate of give a bad no is 64.43% for the decision tree, just shown on the red box. This is AutoNeural 13. This is a decision tree. This is a funnel linear network. This is a funnel tangent edge network. This shows a full classification matrix. Finally, we find the tangent edge is best one. Okay, thank you everybody. This is my email. So if you have any questions, you can send me. Thank you.